Students, we are given this question: if z1, z2, z3 be complex numbers such that modulus of z1 is equal to modulus of z2 is equal to modulus of z3 is equal to r, which is greater than 0, and z1 added with z2 added with z3 is not equal to 0, we expected to prove this result, which is modulus of z1, z2 positive z2, z3 positive z3, z1 divided by z1 plus z2 plus z3 is equal to r. So let us start off with this assumption. It's already given there. Okay, now given that modulus of z1 is equal to r. Now squaring both sides, we get, so what do you get when you square both sides? You get modulus of z1 squared is equal to r squared, but modulus of z squared is actually z multiplied with its conjugate. Okay, so this would mean we have got z1 multiplied with z1's conjugate is equal to r squared. Now from here I can write z1 to be equal to r squared divided by z1 bar. Okay, now this is for the first complex number z1. Okay, also given that modulus of z2 is equal to modulus of z3 is equal to r, hence we can now have z2 is equal to r square divided by modulus of z2 bar, and z3 to be equal to r squared divided by, this is actually r squared, okay, r squared divided by z3 bar. So we have got this representation for z1, z2 and z3. Okay, now having got that, let us consider, okay, now hence we can now, we don't need to have two nows, hence we can now have z1 positive, z2 positive, z3 to be as r squared divided by z1 bar positive r squared divided by z2 bar positive r squared divided by z3 bar. You can have this. Now if I were to take this, the LCM for this as z1 bar times z2 bar times z3 bar, then the first quantity was going to be r squared times z1, in fact it's z2 bar times z3 bar positive r squared times, the second one is going to be z1 bar times z3 bar, the third one is going to be r squared times z1 bar times z2 bar. R squared is common everywhere, so you take r squared out, you get z2 bar z3 bar positive z1 bar times z3 bar positive z1 bar times z2 bar divided by z1 bar, z2 bar and z3 bar. You got it like this. Now you will have to know that the sum of the conjugates, or I would say sum of z1 bar added with z2 bar added with z3 bar, can be rewritten as z1 plus z2 plus z3 the whole bar. Okay, so this is a result. So because of this I can rewrite this entire thing as r squared times, in fact I want to start from z1 z2. Okay, so z1 z2 positive z2 z3 positive z3 z1, they all have got individual conjugates. Okay, so that is going to be the sum of all these components with one conjugate being applied because of this property. Okay, so similarly for the denominator, z1 conjugate times z2 conjugate times z3 conjugate can be actually the product of z1 z2 z3 and the entire conjugate being taken. So I can always do that. Okay, so now on the left side I have got z1 plus z2 plus z3. This is what I've got on the left side. Now what I'm going to do is I'm going to take the modulus, taking modulus both sides, taking modulus both sides, we get, so if I were to take the modulus, this is going to be modulus of z1 positive z2 positive z3 is equal to modulus of r squared times z1 z2 plus z2 z3 plus z3 z1. The entire conjugate has to be there, placed within the modulus, divided by z1 z2 z3, the entire conjugate bar being placed. So this is what we have got. Now you have to understand that we have a property, modulus of z1 z2. You have something like this, then this can be equal to, okay, I can rewrite this, to be as, this is to be as product of the quantity z1 with its modulus multiplied with z2. So I can always write like this. Okay, remember that. So what I'm going to do, I'm going to use this property, that is modulus of z1 z2 is equal to product of the modulus. So by this property I'm going to break this. So this is going to be equal to modulus of r squared times modulus of z1 z2 z2 z3 plus z3 z1. Of course they have a conjugate. I'm pulling the modulus down, okay, divided by z1 z2 z3, the entire conjugate bar being present on that. I'm using this property to break this quantity as r1 squared modulus and the modulus of this entire quantity. Okay, so we have got this. Now we are clearly given that r is greater than 0, so this is going to be equal to r squared, right? This modulus is going to be always positive, so I can just simply place r squared there. Now also we know that the modulus of the quotient is equal to the quotient of the modulus. Okay, this is the property. We know that since modulus of z1 z2 is equal to mod z1 divided by mod z2, I'm going to break this as mod of z1 z2 positive z2 z3 positive z3 z1. Of course place the conjugate bar, and this is divided by modulus of z1 z2 z3, the conjugate bar. So this is what I've got. But you have to know a very important property. So what is that? Now we know that the modulus of z is same as the modulus of its complex number, its conjugate. Okay, so because modulus of z is equal to modulus of z bar, I can rewrite this as r squared times modulus of z1 z2 positive z2 z3 positive z3 z1. So I can do that, divided by, for the denominator this is going to be modulus of z1 z2 z3. But as I mentioned to you that modulus of z1 z2 is actually equal to modulus of z1 multiplied with modulus of z2. So because of this property I can rewrite the denominator as modulus of z1 multiplied with modulus of z2 multiplied of modulus of z3, and the numerator I can just retain it as it is. It's going to be modulus of z1 z2 added with z2 z3 added with z3 z1. So this is what I have got. Of course we need to place the right hand side also. So on the right on the left side we've got modulus of z1 positive, z2 positive, z3. Okay, it's a modulus sign. Now given we were given that modulus of z1 is equal to r, and that is also the same for modulus of z2 and modulus of z3. So all of these are equal to r. So because of that, I can rewrite this to be as r squared times modulus of z1 z2 positive, z2 z3 positive, z3 z1 divided by, this is r multiplied with r multiplied with r. So this is equal to r squared times z1 z2 plus z2 z3 plus z3 z1 divided by r cubed. Okay, this is r cubed. On the left it's modulus of z1 plus z2 plus z3. Now r squared and r cubed, they can get cancelled, giving me modulus of z1 z2 positive, z2 z3 positive, z3 z1 divided by r. On the left it's z1 positive, z2 positive, z3. I can move r on the left side, I can move it up. So this is going to be modulus of z1 z2 positive, z2 z3 positive, z3 z1 divided by modulus of z1 positive, modulus of z2, in other words modulus of z1 positive, z2 positive, z3. This is going to be the case, but we know that modulus of z1 divided by modulus of z2 can be rewritten as mod of z1 divided by z2. Okay, so this is going to be mod of z1 z2 plus z2 z3 plus z3 z1 divided by z1 plus z2 plus z3. On the left it's r. This is what is required. So hence you can state, hence, okay, the result is proved. Okay, so that completes the solution to this question.